What we've seen so far is the similarity between Coulomb's law for two charges and Newton's law of gravity for two masses. We know that the form of the attraction looks very similar for both of them. In the first semester, we used little g, and that represented the force of Earth's gravity on a given mass. We could have represented this in newtons per kilogram instead of meters per second squared. Either way would be okay. Here we're going to define capital E to be the electrostatic force on a particular charge. We could do everything with Newton's second law, sum of the forces equals ma, and use E times Q to be our force. But it turns out, just as in Physics 1, some problems are easier to do in terms of energy rather than forces. So back in Physics 1, when we looked at gravity, we had a simple form for gravitational potential energy, and we said it was mgh. Then we went to real Newtonian gravity, and we weren't using F equals mg anymore. We were using gmm over r squared. We'd had to define a new potential energy that would fit that new form of the force. If you look in your notes, you'll see that we wrote that potential energy as U equals negative gm1m2 over r. And pay attention to the fact that that's not r squared, because that would be force again. Also, the energy is negative. What that means is we'd have to put in some energy to separate these two masses further apart than they are right now. It also means the only way the potential energy between them would be zero is if we move them infinitely far from each other. The electrostatic version of this is very similar, except we don't have to worry about putting the negative sign in by hand because it's already taken into account. We have the constant from Coulomb's law, and then the two charges that we're talking about, and again the distance between them, and it's not squared. Here, if the two charges are opposite in sign, we'll get a negative energy automatically. If they're the same sign, we'll get a positive energy, meaning they want to push away from each other. Now, we can consider the field to be the force per charge. We can also define a potential energy per charge or per mass. We would call this the gravitational potential or the electrostatic potential, depending on which one we're talking about. But that's not really a great name for it because it's very easy, especially in the beginning, to confuse potential with potential energy. Unfortunately, that is the correct term for it, is the potential. You almost certainly never did anything with gravitational potential in Physics 1. If we were going to use mgh as our potential energy, the gravitational potential would just be that divided by m, or gh. If we use the same approximation that we used to get little g in the first place, which is gravitational acceleration is constant, we'd get rid of the little g and we'd say height is equivalent to gravitational potential. If you've heard the phrase water seeks its own level, that's what's really happening here. We look at all these weirdly shaped containers and the fluid in them is all at the same height. The reason is the surface of the fluids are at the same height because the surface of the fluid is an equipotential. All parts of it have the same gravitational potential. So here, since little g isn't changing, all parts have the same height. This is really one of the only two uses I know about for gravitational potential, but the other one is really pretty cool. It says that the rate of flow of time in a gravitational field depends on the gravitational potential, and we might look at this for a minute at the end of the course if we look very briefly at the general theory of relativity. Problem is, that's so complicated that even Einstein spent 10 years working on it before he was able to understand it enough and publish it. Anyway, one of the common symbols for potential is this Greek letter phi. We're going to find that electrostatic potential is much more useful for us, and that's what we'll look at next.